Nature is nonlinear. Nature is mechanics. Nature is composite. Nature is structured. In short, nature is the dance of nonlinear mechanics, of composite structures. प्रकृति गैर रैखिक है, प्रकृति यांत्रिकी है, प्रकृति समग्र है, प्रकृति संरचित है. संक्षेप में प्रकृति समग्र संरचनाओं के गैर रैखिक यांत्रिकी का नृत्य है. भूमिमंगलम भूमिमंगलम उदकमंगलम उदकमंगलम अग्निमंगलम अग्निमंगलम वायुमंगलम वायुमंगलम गगनमंगलम गगनमंगलम सूर्यमंगलम सूर्यमंगलम चंद्रमंगलम चंद्रमंगलम जगतमंगलम जगतमंगलम जीवमंगलम जीवमंगलम देहमंगलम देहमंगलम मनोमंगलम मनोमंगलम आत्ममंगलम आत्ममंगलम भूमिमंगलम उदकमंगलम अग्निमंगलम वायुमंगलम गगनमंगलम सूर्यमंगलम चंद्रमंगलम जगतमंगलम जीवमंगलम देहमंगलम मनोमंगलम आत्ममंगलम सर्वमंगलम भवतु 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 सर्वमंगलम भवतु 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 सर्वमंगलम भवतु भवतु भवतु.
Good morning, everybody. Can you see this slide? Okay, thanks, Pramay. Let's go ahead. So today is the 10th class. So as promised, we'll just look at the lead actors that we are going to deal with in this course. The same set of lead actors that we dealt with in the flight vehicle structures course, just that we are going to deal with them in a more stringent manner this time, especially in terms of their relationship between each other, more complicated relationships, which we summarized in the previous course, but we will derive in this particular course. And in terms of relationships, you always have challenges. So how do you go about resolving those challenges, especially in terms of conflict situations? How do you come up with a conflict resolution plan? So that's essentially what we'll be looking at, which means that this is like almost like quick fire round of flight vehicle structures. We'll essentially be looking at pretty much the same kind of slides that we saw towards the second half of the course, but we'll go through in a rapid fire way, especially pointing out to the main differences that are going to be there between the way we approached then and we approach now. Because in that course you also did a lot of homeworks in which you made quite a few assumptions which we would normally not want to make in a course like this. So we will point out some of those subtle differences as we go along. So in the end of the previous class, we looked at a few questions in terms of what are the four lead variables which describe the state of any mechanically loaded system, and it could also be thermally loaded, but essentially any loaded structure. What kind of variables do we deal with in analyzing it or designing it? That's essentially what we looked at first. That was the first question, and the answer to that question, as you already know from the previous course, is the set of four variables, wherein we talked about mostly in terms of how things vary with respect to space, but it also includes, of course, the way things vary with respect to time. So instead of strains, we also have along with strains, we also have velocities. And strains include curvatures and velocities include angular velocities. And similarly, instead of stresses, we had momenta, wherein these stresses include, of course, the stresses due to bending, which are torsion, as well as those which are directly like pressure loads or other kinds of tensile loads. So similarly, the momenta can also be those which are translational in nature and those which are rotational in nature as well. So these are the four types of quantities which describe the mechanical state of any structure: loads, stresses, strains, and deformations. The loads are inevitable in the sense that because the structure is in a certain environment, therefore the environment interacts with it, and therefore it's not possible to completely isolate it. The best example you can have of such an isolation is in a satellite, let's say, in free space rather than in any particular orbit. If you have a, let's say, like a free beam. So in other words, the boundary conditions are all that it's just free. So what happens to a free beam like this, just floating in space, not orbiting any planet or in any star, just that it is just floating around in space? Essentially, it's pretty much like vacuum, and therefore there are no stresses which are acting on any of its surfaces or ends, which means that there is no load boundary condition, but it's just free to undergo any kind of displacement or deformation. So in such a situation, you see that though it's kind of floating around, once in a while it can get hit by any space debris, or it can go and hit any other debris that might be floating around, whatever. But those are instantaneous loads that are there, which can occur once in a while. So such things are inevitable, but the way this structure is in terms of its boundary conditions as a free structure does not have any kind of stress or strain, and in other words, its deformation is more of a response rather than a reaction. So that's essentially the difference that we will look at: a response. So these are certain things that we didn't look at in the previous course. So I'm trying to bring in certain subtleties that are involved in this overall refined way of doing things. So response versus reaction. So this is essentially an output that we are talking about over here, whereas the input is, of course, your load on the other hand, and that's essentially what is coming from the environment. Of course, you can also have internal loads, but more often than not, we are dealing with these external loads, and therefore it is essentially an environmental input that is coming. As we saw in the flight vehicle structures course, it could be aerodynamic loads, etc. We'll not go into those details because I was also keeping in mind the larger audience we had in the flight vehicle structures course, where people who are not going to specialize in structures are there, and therefore I talked a lot about flight mechanics, I talked about aerodynamics, propulsion aspects, etc. Here we'll have a much of a focus on what we are going to deal with, namely the structures, and I can talk of a little more intricate aspects of structures which would have been beyond the scope of the previous course. So the essential thing to remember is that out of these four entities that you have, which are loads, stresses, strains, and deformation, the loads are inevitable and is the input, and the deformation is what is the response of the structure if it's more like a free structure which is not having any stress or strain. So in other words, it's essentially having just the input and the output alone, the loads and the deformation alone, without having to undergo any internal turmoil. So this is very similar to what we go through in life as well. Pain is inevitable, but suffering is optional. And suffering starts with an S, just like stress and strain. So stress and strain result only when you have certain kinds of boundary conditions, and the internal mechanisms are not able to cope up with the kind of pressures and the shears, which is shear is nothing but friction. So frictions and pressures that are coming from the external environment. So while you're looking at this from the point of view of an application to a mechanical structure, here, you can see the beautiful parallel that we have between life and this, because that will enable us to understand this more deeply, and in the problems that you're working also, it will give you a different perspective which other people, other researchers would not have got that kind of a perspective. So that perspective that you get by total involvement with your structure in terms of how it behaves and how you behave under similar kind of situations from the environment, that will help you understand and resolve this problem in a much more useful way than what others could do without this kind of an insight into the problem. So essentially, remember that the loads are inevitable, but the stresses and strains are optional. So similarly, your pains are inevitable, but the suffering is optional. So this suffering is essentially an imaginary thing that we are encountering because of the stresses and strains. Similarly, the stresses and strains are two-dimensional tensors, which are point functions. They are functions of the x1, x2, x3 location, spatial location, and the time instant at which you're considering this particular stress or strain. So essentially it's a point oriented thing, and we know that as we shrink to a point, anyway the classical mechanics is not valid. The classical mechanics is a continuum mechanics subject which is valid only under larger length scales, but when you're dealing with stresses and strains, we are dealing with point functions which are essentially not going to be of much of reality, but these imaginary things help us to connect the input to the output. What is the response that is going to be? And I talked about response versus reaction. A reaction is typically a situation when you involve the stresses and strains rather than without the stress and strain. There's a direct relationship between the load and the deformation. Then you're talking about essentially a response where you're talking of something that you do naturally rather than involve what you think the structure is made out of, which is essentially this particular thing about the material that is involved. Because what you are made of, you think that you are, and then therefore the stress comes in, the strain comes in, and instead of giving a response, you give a reaction. So whether it is the structure or whether it is you, it's essentially the same thing that is happening in both these cases. As we saw, the relationships now, the green colored ones, which is between the loads and the stresses, is your equilibrium equation that you see over here. Then between the stresses and the strains is your constitutive law, and between the strains and the deformation is essentially your kinematics that is going to be there. In addition to this, this is essentially what is happening in a generic sense, and then there are the boundaries where you tend to start distinguishing between yourself and the environment, or between the structure and where it is operating. So that boundary is going to have certain boundary conditions, and here we are looking at boundaries both in space and time. When we are talking about spatial boundaries, we are talking of boundary conditions. When we are talking of temporal boundaries, that is when it starts, when it ends, etc., then you are basically talking of so-called initial conditions and final conditions, which we'll encounter when we look at Hamilton's principle, where the functional is defined as an integral between t1 and t2, where t1 is some initial time and t2 is some final time, the time duration during which you're considering analyzing or solving this particular problem. So essentially, you are going to have, in addition to what is there happening at each and every point of the structure, there are certain things which are happening at these interfaces between the environment and the subject of interest, be it the structure or be it you. So that's essentially what we call as the boundary conditions, but in a time-dependent problem, it could also have the initial conditions at both the ends. What do the initial conditions in the natural sense mean? They could be that you're starting off with a particular load. For example, you're subjecting a particular supported structure with an instantaneous load like this, and then it starts vibrating probably at one of its natural frequencies. So that is your initial condition, the load that you have applied. Similarly, that initial condition, instead of being a load, it could have been in terms of a displacement as well. So for example, I take something and give it a certain displacement and then drop it. So essentially it is falling down. So I've given it an initial displacement. So what is its u to start with? So that's essentially what we are talking about here. Of course, I'm demonstrating with rigid bodies, but the same thing can be extended when you're talking about flexible bodies as well. These are two extremes that we look at: rigid bodies where you have infinite stiffness, and you have fully flexible bodies where you do not have any restriction, constriction, or even boundary conditions. So which is like the free beam that I talked about in outer space. So essentially what you're talking about there is there is no stress or strain that is involved at all. So you have two extremes, but most of the time we are not studying these two extremes because these are the outliers, those who have understood life and therefore have gone beyond all of these issues, just like that free beam floating in space. So it's gone beyond that. So either one of these two extremes, that's a rigid body, which we know in real material world doesn't exist. There's no such thing as actual rigid body. Yes, one body might be much more rigid compared to another body. For example, this could be more flexible, whereas this could be harder, and therefore I can say with respect to this is a rigid body. But you know that this can also undergo certain stresses and strains. In other words, it's flexible. So anything which is made out of material stuff is essentially going to undergo these stresses and strains, and that's why the relationship between the stress and strain is essentially a material relationship that you're going to be talking about. So that's essentially what we say, that at the four-dimensional level, which means that x1, x2, x3 and time, at that of course x1, x2, x3 need not be a Cartesian system. It could be let's say a cylindrical system, or it could be a spherical system, or any arbitrary curvilinear coordinate system, but essentially three which are not collinear or coplanar. And then of course you have time, and all of these is the canvas on which this whole painting or dance is going to take place. It's painting in a statics problem, and dance is essentially in a dynamic problem. So if you see any guest waiting, do admit them in case I miss it out. So just if somebody else knocks in as well. So everybody is welcome. So what we are talking about essentially is that these three sets of equations that you have, the equilibrium equations and natural boundary conditions on the one hand, the kinematic and geometric boundary conditions on the other hand, and in between the constitutive law, at the four-dimensional level of three spatial and one temporal, have certain pure dependencies. But once we do this dimensional reduction to either from 3D to 2D or to 1D, of course the ultimate would be to do it to a 0D, putting everything into a point, which is essentially again that outlier case that we are talking about, you can, instead of doing a dimensional reduction, you can do exactly opposite. It's a reciprocal way of doing things, where you're treating only the higher order terms and then coming to the lower order terms. In other words, the leading terms comes later. So that's an opposite way of approaching the problem, which nobody has approached, and that's again a huge body of potential research that we can accomplish, where we are going, instead of dimensional reduction, dimensional expansion. And so in other words, we have a four-dimensional problem because of three spatial and one temporal dimension. Now we start expanding those dimensions, go to an infinite dimension, which is again liberation. So either you go from the 4D, which is a finite problem, to a 0D, or you go to which is essentially nothingness, or you go to an infinite dimensional, which is everythingness. Either case, it's essentially liberation that you're talking about, whether it's for you or for your structure that is involved. So they're very, very interesting problems that we can probably talk off the camera, offline about these aspects, which can be far more impactful than any of the simpler structural problems that we typically deal with in our research. So what we see at this four-dimensional level, that is either before dimensional reduction or before dimensional expansion, is a situation where there's a certain kind of a pure dependence. And this pure dependence is on certain aspects, keeping in mind that the loads actually, if you look at any structure, you might be defining a concentrated load like a force, or a concentrated moment like a let's say a tip moment in a beam, or it could be in a shaft, a tip torque. So whether it's a torque or a moment or a concentrated force, all of these are idealizations. You can never ever really apply a concentrated force or a concentrated moment, be it for bending or for torsion, because if you do, essentially what it means is you are applying finite force at zero area, which means that at that particular boundary you have infinite stress, and you know that the material cannot deal with infinite stress. So there's absolutely no way, either in practical experimental work or in your imaginary situation, you applying that just for the sake of simplicity or for the ease of modeling. People assume a concentrated force. There's no such thing as a concentrated force, a moment, or a torque. They're all distributed. And I've given that example of that many a times in the case of the aircraft, where people usually take the engine loads as concentrated loads on the wing. But the engine load, which is essentially a thrust and a weight of the engine, which is acting at the pylon, is not acting at a point. It is acting actually at a surface, because the pylon has a finite surface area. It's not zero surface area where it is attached to the wing. And therefore, the load, whatever is coming due to the thrust and the weight of the engine, and also the moments due to it, because they are acting at different locations from where it is attached, the moments coming out of it, all of these are distributed over that surface area of contact that the pylon is having with the aircraft wing, if it's attached to the wing, or if it's attached to the fuselage. So essentially, in reality, none of these loads are actually concentrated loads, but many a times people define problems in terms of concentrated loads, and therefore we have to take into account in a particular way, and in which case the load versus stress starts depending upon that particular area. Otherwise, the boundary conditions that are there, the natural boundary conditions, would have to be described in terms of stress boundary conditions. What is the traction that is taking place at a particular location? So for example, if I'm keeping my elbow on this particular table over here, and then essentially there is a certain finite contact surface area that is there, because some of you are working on contact mechanics problems, or may not be posed exactly as a contact mechanics problem, but as Kaja has given insights to that particular person, it could be essentially a contact mechanics problem. So essentially what is happening in that contact surface area is there is a normal force, and there is if there is a movement, there is going to be a frictional force as well, which is a kinetic friction. If there's none, then just to begin the motion, you're going to have a certain static coefficient of friction, which is also going to result in a shear stress. But essentially it's either a normal, it's a combination of normal stress, and it could be a shear stress. Of course, if it's lubricated surface or whatever, then that might be negligible, the shear loads. But both these boundary conditions, you can see, are not in terms of concentrated forces, but essentially they are distributed forces. So truly speaking, you should be describing them in terms of the stress, the normal stresses, either compressive or tensile, and the shear stresses that are there in that contact region. So when you're talking about stresses like that, then you can see very clearly that the way you are describing this load stress as an equilibrium equation is essentially not dependent on the geometry. But once you describe concentrated force and then you take Saint Venant's principle, of course, because the concentrated force cannot be dealt with, it's infinite stress and the material is not capable of it, so you go a little bit inside, which is of the order of a few cross-sectional dimensions. So it's, let's say the diameter is d, some n times d, you go in between. So from there, it doesn't matter how the load is applied. Even if it's a concentrated load, you can think of it as a distributed load, and that's the same effect it's going to have in the interiority. So most of the time our solutions are working only for the interior regions of the structure, not at the boundary itself, because of the fact that we are not defining the boundary condition in realistic terms. We are defining it in more idealistic terms, in terms of these concentrated loads. But our methodology will be applicable. We will, as you know, you've got the previews of this in the previous course. We can deal with not only distributed loads but also these concentrated loads. But it's always helpful to know that these concentrated loads are an idealization, and it's because of those existence of those concentrated loads. Eventually, we talk about the equilibrium equations depending upon certain geometric features like the cross-sectional area or the cross-sectional moment of inertia or the cross-sectional torsional constant J that is important in torsional problems. So all these kinds of things arise in the equilibrium equations if and only if we are dealing with these idealized situations. But in realistic situations, the equilibrium equations are just essentially Newton's third law, which is every action is equal, has an equal and opposite reaction. So essentially the surface on which you are applying certain boundary conditions is actually reacting to that, and therefore the stress is happening. If it's not reacting to that, it's just responding to that, then you can probably avoid the stress and the strain, directly go to the response. So here we are talking of these so-called natural boundary conditions, which are expressed in terms of the forces or moments or their distributions. On the other hand, with the kinematics, along with the kinematics, you have certain boundary conditions which are essentially expressed in terms of the displacement or rotations or the velocities, etc. So next, if you are not doing all that, you're doing everything realistically and in the four-dimensional space before dimensional reduction into a beam or a shell or into a particle, also the zero from 4D to 0D. Or you're going from 4D to 5D, X6D, and so-called ND problem or infinite dimensional problem also as the extreme. When you're doing that, then this purity is lost. You still have this dependence on these aspects, but things can get mixed up, as we saw in the previous class itself. 3 examples, which we'll again rush through this time as well. So I'll point out once again that yes, even though the constitutive law is supposed to depend only on the material, it starts depending on the geometry. The equilibrium equation is supposed to depend only on the physics, only on the momentum conservation principle, but then it starts depending on the geometry. Why? Because of all these jugglery that we are doing just to for idealization purpose and for keeping things tractable and simplified, or just by way of habit, because somebody else has been doing it that way for a long period of time. We also continue doing it that way, thinking that's the only way of doing it. But there could be this is the question of being out of the box and in fact recognizing that there's no box, and therefore being open to far more superior ways of doing things, far more refined ways of doing things. So the conservation law in particular, of course, in this case, what we are dealing with here is the conservation of both the translational momentum and the angular momentum. But once the external loads come in, it's the rate of change of that momentum which is equal to the loads that are coming in. Once again, they could be the translational loads in the form of forces, or both concentrated as well as distributed, or they could be the rotational forces, which are essentially moments. So whatever it is, we call it force, just in a generalized sense, just like we call the velocities also as strains in a generalized sense. Then so that's the conservation law. Then the material dependence is over here of the constitutive law. What we are made out of, essentially those panchabhuta system that we are made out of the panchabhutas, the space which is essentially a space time is already taken out as a canvas and put together. And then there's this energetics that we are talking about, the energy, which is the third panchabhuta. So you have earth, water, then you have fire, and then you have air and space. So space is already gone out as space-time, which is essentially the domain on which you're operating, the structural domain and its immediate boundary, which is going to give you all the boundary conditions. Now the third of them is the energy, which is or the fire, which is again removed, and that's essentially what is coming through in your constitutive law as your strain energy, or basically something that is making the structure do certain work. So either externally or internally. So that's essentially that's gone. So then you're left with solid, liquid, and gas. Unfortunately, though we would like to do all of that together in a continuum mechanics, that takes too much time, and therefore we have divided this and sent off the air part to the gas dynamics people and or aerodynamics people, and the fluid to the fluid mechanics or hydrodynamics people, and we deal only with structure. So such a simplified problem we actually have, just the earth element that we're talking about, the solid element that we are talking about, that we are essentially dealing with. But whatever it is, whether we are dealing with a structural mechanics problem or a fluid mechanics problem, in which case it could be either liquid or a gas, the thing is that this particular relationship that is there at the material level is what we call as the constitutive law. Because why constitutive? You've heard the word constitution, the Indian constitution, for example. In the previous course, in the middle of that, we had the Constitution Day where we read the preamble also. What the word constitution means is what it is constituted out of. So constitute essentially is a verb, and then constitutive is the adjective which is formed out of that. What constitutes something is what it is made out of. So for example, when you're cooking a khichdi, for example, what are the ingredients that go into it? That's essentially what it is constituted out of. What we are interested in here, of course, in this course is composites, where we are talking of our khichdi being made out of fibers and matrices. So healthy khichdi because of fibers there. So the what we are talking about is essentially how each one of their constitutive laws then because the fiber itself is made out of certain things, the whatever it could be a molecule or it could be an atom. For example, in the case of glass, it could be a molecule that we are dealing with, or a Kevlar. On the other hand, with the carbon fiber, you're actually dealing with atoms having a certain kind of an arrangement because of the way it is drawn into the fiber form. There's a more regular arrangement than in amorphous carbon. Exactly the difference between amorphous carbon and diamond, for that matter, even when it's not drawn in the form of a fiber, you see essentially the qualities improving in terms of the mechanical properties and a few other non-mechanical properties as well. But essentially what you're talking of is something that arises out of the constituents material properties, and therefore how the overall mixture, be it an alloy mixture in a metal or be it a composite, whatever kind of matrix it might be in, essentially are mixtures which are going to have some kind of a combination of properties of their ingredients, just like the khichdi is going to taste partly like the dal and partly like the rice that you add into them. Now that's at the four-dimensional level. But in this course, nonlinear mechanics of composite structures, being in the aerospace department, will predominantly be dealing with beams, though we would also like to deal with shells, and once in a while we will talk about some of these two-dimensional problems as well, and many of you are working on it. So in the one-to-one interaction that I plan to have, and which Kaja is already having, thankfully, with many of you, so that's essentially you could be dealing with two-dimensional problem. But whether it is that or in the course we'll predominantly be dealing with the one-dimensional beam problem, because it's a more complicated problem, because you have to go from this 4D to essentially what is a 2D problem, because if you take time into account, in spatially speaking, of course, you're going from 3D to 1D, but with time, which is not going to be given up in a dynamic beam problem, you still have a two-dimensional problem over there. So when you're doing that, then yes, this constitutive law starts depending on things other than the material, in particular the geometry, as we shall encounter. And that dependence on the geometry was brought in very simplistically in the previous course, in the form of EA, GJ, and EI as the extensional stiffness, the torsional stiffness, and the bending stiffness, wherein the geometric feature was in the form of the area and the torsional constant and the moments of inertia. Area moments of inertia, to be very specific about that, because there's something called the mass moment of inertia also, which we deal with in the dynamics problem, that is of critical importance over there, where the time dependency is brought into picture. So, but in the four-dimensional problem, they're all purely material properties, the constitutive law. But once we go into either the beam problem or the shell problem or a particle problem or a dimensionally expanded problem, in all these situations you're going to bring in something from the other aspects. Something is going to spill over from either the equilibrium equation or the kinematics or both. Now that we are dealing only with composites, the only difference that is going to be there between the way we approach the problem and the way others approach the problem, as I've described in far more detail in lecture number 17, or rather 18, 17 or 18, in the flight vehicle structures course. There's a series of videos in which we go through all of these problems, which we will just skim through very quickly in this, more as a revision, because it's been 4 months since we did that, probably end of November or early December that we did that. So very, very quickly we will grasp through that, but more pointing out the subtle differences of how we approached then and how we will approach now. So essentially, when you're talking of the composite as opposed to a metal, the only difference is going to come in the constitutive law as far as the original problem, that is the 3D problem along with time 4D problem is considered. But once we dimensionally reduce it, then of course the other things are going to change as well. But to start with, because that's going to be the starting point for the variational asymptotic method, where we are going to have the energy functional, which we are going to minimize. It could be starting from the Hamilton's principle, for example, where there's a functional involved, which involves the Lagrangian, etc., which is made out of the kinetic energy, it's made out of the potential energy, and then you're trying to minimize that functional, bring it to a certain stationary value. That stationary value again, remember that the strain energy, for example, when you're minimizing, it's made out of even in the simplest case of a linear problem, it's made out of the strains, quadratic in the strain with a stiffness matrix in between. And that stiffness matrix, one of the many properties that matrix has is that it is positive definite. When it's positive definite, it means that whatever the strain values, as long as they are not all zeros, you're going to get essentially a zero, essentially a positive value for the strain energy. But if all the strains happen to be zero, then you get, of course, the strain energy to be zero as well. So in any case, the strain energy is always going to be positive or zero. So if you're having a stationary principle where essentially you are actually minimizing this that energy and coming to the lowest value it can have, the lowest value that you can ever think of is zero. So that's essentially those outlier problems that we are talking about in life as well as in terms of liberation, or you're talking of because you're actually not checking whether it is minima or not, you're just doing a stationary principle, it could end up with a maxima, and in the maxima case the outlier value of course is the infinity value for the strain energy, which is again another different way of approaching liberation, either from one end or the other end. So that's essentially what's happening, but it's essentially going out of your understanding that you are a material and therefore bounded by a certain constitutive law. It's only as long as you think you're a citizen of India, you're bound by the Indian Constitution. So if you have given up the citizenship of India, taken up this American citizenship, for example, you're no longer bound by the Indian Constitution, you're bound by the American Constitution. So essentially, if you break through all of these constitutions, so then you are no longer in the material world, you've realized that you're beyond the material. So that's essentially what we talked about in the beginning of that free beam floating in space. It's essentially out of the gravitational fields, or at least it's in a negligible gravitational field, because the gravitational fields that we normally are in the Earth, or to some extent the moon and the sun as well. So all these effects are no longer felt by that particular thing, and therefore it is stress-free kind of a situation, even when all kinds of things come and knock on it. So yes, the pains are inevitable, but the suffering is optional. So stress and strain are optional, as even a simple thing as a free floating beam shows us. So that's essentially what we are talking of in a difference between a composite and a metal over here. So because amongst these three relationship sets, it's very clear that the conservation laws depends entirely on the physics of the problem. The kinematics and the geometric boundary conditions depends entirely on the geometry. It's only the constitutive law which depends on the material, and therefore it's the only thing which can cause a difference between analyzing a metallic structure on the one hand, which one of you wanted to do, but please avoid that because it's a composites course, so try to deal with composites. If you want to deal with metals, fine, you do both, and then compare and show that the composite is doing better than the metal. So bring in some flavor of what the course is into this. So don't deal with a purely linear problem, for example, because it's a nonlinear mechanics of composite structures course, and don't deal with just metal alone. If you want to deal with metal, well, deal with a metal matrix composite instead. Put some fibers into the metal and make it a metal matrix composite, and then deal with it. So so I'm not mentioning the name over here, but whoever it is, you know that. So please try to enlarge the scope of your problem to bring in a certain flavor of this, because otherwise one thing is, of course, it's not in the flavor of the course, this doesn't fit into this course, that kind of a work. But more importantly, for your own good, because something like that is so simple with either a linear problem or a pure metal based problem, that the chances of it getting published with this kind of an approach is going to be very minimal, because these are problems that have been done many decades ago. So you're not going to get much benefit out of doing that. So that's the reason why I'm saying that in terms of the probability of it getting published also, it will be much better if you can bring in a little more of the complications that are useful or have not been done already. So there are two main reasons why composites and metals differ from each other. Of course, there are many other subtle differences, but many of them can be pointed out to this original difference in the very way these structures are made and the original behavior that they have. One is a point-to-point difference. The other is at a point direction-to-direction difference. That's all that makes the composite different from the metal. So it's not a whole lot complicated as people think, because there are ways to handle these two complications, as we already know. So the first difference is the heterogeneity, or what we call as non-homogeneity. So that's the material is the overall structure is made out of multiple materials. But that's the case, as I explained in the previous course, also with the bimetallic strip, where you're having two different metals. That's also a heterogeneous problem, but that's the simplest heterogeneous problem you could probably think of. But even an alloy, for that matter, is. But again, there are no physical identifiable interfaces unless you go to very low length scales where you can look at the grain boundaries, etc. Whereas in the case of a fiber matrix composite, even at the micron level, which is not a very small level like nanometers or at the atomic or subatomic levels. So essentially you have those clear interfaces where there is a certain boundary condition between them at the interface, and therefore that can cause the heterogeneous construction of these materials to manifest itself in various non-classical ways that are important to analyze. So essentially what non-homogeneity is that the properties are varying from one point to another point, because at one point you might be within a fiber. If you move away, you can be in another fiber, in which case of course it's the same problem, but in general you can be in the matrix also, or in a void, or in an additive, and each one of them would have their own properties, and therefore there is a heterogeneity associated with that. So that's one complication. The second complication is because of anisotropy. So isotropy, tropy means direction, iso means same, and an means not. So not the same property in different directions. So that's the generally anisotropic situation. But thankfully, as we saw in our list of assumptions, there are two assumptions which make it not as complicated as a generally anisotropic problem, not as simple as an isotropic problem, but somewhere in between, namely orthotropic, which means given properties in three directions, I can determine in any other fourth direction, as long as those three directions in which I were given the properties, because of the way it is defined, is orthotropy, is that three orthogonal directions. So if I know the properties in any three orthogonal directions, I can determine in a fourth direction quite easily. And typically we choose those as the principal material directions, one along the fiber and the two perpendicular to the fiber. Now again, these two directions, the properties would have been different if the fiber geometry was like an ellipse, which for example is an example that some of the researchers consider, including in our lab like Rajesh. So but in that case, along the major axis and minor axis, the properties could be different, and therefore you do not have the second simplification that we looked at, which is transverse isotropy, that is in the plane perpendicular to the fiber, the properties are same in all the directions. So that is an additional simplification we have. But in either case, even after the introduction of these simplifications, valid simplifications of orthotropy and transverse isotropy, you're still dealing with an anisotropic material. In other words, not as simple as an isotropic material, where you could do the entire constitutive law in terms of just two variables, namely the Young's modulus and the Poisson's ratio, or instead of Poisson's ratio, the shear modulus. Instead of the E nu combination, you could have the lambda and mu combination, which is the Lamé parameters, but essentially two independent parameters that you could deal with. Whereas in composite, even after introducing the orthotropy and introducing the transverse isotropy in the plane perpendicular to the fiber, you still have more than two variables to deal with, but still it's much more manageable than dealing with infinite variables, which is what truly generally anisotropic material means. So essentially property varying from direction to direction as opposed to point over here. Okay, at a given point, direction to direction, in a given direction, point to point. So this is both complications hitting at us simultaneously, but there are ways to handle that, and as we already saw, the way the heterogeneity is handled is by, instead of dealing with stress and strain as point properties, yes, they're still point properties, but the way their numerical values are arrived at is just by having a volume averaging over a certain minimum volume that you need to take, which is typically known as the representative volume element, or RVE. So we define a quantity called the RVE, which is not necessarily the unit cell. That's very important to remember. Many people, even in publications, senior researchers use these terminology interchangeably. Representative volume element on the one hand, and the unit cell on the other hand. The representative volume element is a collection of unit cells. Unit cell is the simplest geometric entity that you can go to into the entire structure, and which is occurring in various places within the structure. But the representative volume element is essentially talking about a collection of those unit cells, which in that sense, when you are averaging it out, then within that layer, when you're going from one point to another point, you're not going to have the material property differences. So that's essentially identification of the RVE, and within that RVE, the representative volume element, you are going to have some kind of an averaging out of the quantities of interest, namely your stresses and your strains. Now you average it out. So still it is a three-dimensional variable and also a function of time. Both these stresses and strains, and both are second order tensors, even after doing this volume averaging, because if you want to get at a particular point, you take an RV around that point as the center in some sense. It could be the centroid, for example, the volume centroid, or and if you even look at a slight 1 micron distance away in a particular direction, then you take a new RV which is centered around that. So the new centroid has changed. The RV definition may not have changed, but your still centroid has changed, and therefore you are having an equivalent homogenized material, which is an imaginary material, in which the stress and strain dependence between each other is in this particular manner. Now, if we actually calculate those stresses and strains, do they have any significance? By themselves, they don't. It's only when you know the stress or strain in the actual heterogeneous structure of what the stress in the fiber is or what the stress in the matrix is, you'll be able to say certain things about how the fiber deforms, how the matrix deforms, etc. But for a dominant variety of problems, so probably 99% of things that we deal with either in academia or industry, we are not really concerned about that unless failure sets in and we want to delay that failure or avoid that failure. We are not dealing with those kinds of issues, and therefore it is okay to deal with this equivalent homogenized structure, knowing that these stresses and strains that we are talking about are all imaginary quantities. What really matters is, for a given load, what is the deformation that is setting in, and therefore we need to understand the overall response of the structure, how the overall shape of this structure changes, how the overall size of this structure changes, and how that impacts on the load itself changing again. For example, in a aircraft wing, because of the overall change in the wing shape, you can have the aerodynamics changing, and therefore the aerodynamic loads like the lift distribution, etc., changing, which in turn again, so it's a cycle that essentially happens, and an equilibrium has to be arrived at in that through an iterative scheme in the mathematical model. So that's essentially how you deal with the heterogeneity, by defining the volume average stresses and volume average strains, and always remembering that that's what we are dealing with. They're not the actual stresses and strains. So already in terms of the stress definition itself, many people are not dealing with the true stress or the Cauchy stress. We are dealing with a stress defined upon the original reference configuration, but the area itself is changing, and therefore that's the reason why, as I pointed out in answer to one of the questions, the stress strain curve is actually coming down, even though it could be still within the elastic regime, which means that for a given value of stress, you could have potentially two possible strain values. One of you is working on a bistable configuration. So of course, this is not what I'm talking about, is at the material level at a point, whereas that person is dealing with at two different configurations of the overall structure. But essentially, that's what we're talking about. So there, what that person is dealing with is a realistic kind of a situation in an actual structure in which the problem is occurring. Whereas what we are talking about over here in a stress strain curve turning around in the elastic regime, if at all it happens, you see, then obviously you're not dealing with the true stress, and that's the reason why you're not taken into account that the cross-sectional geometry of the specimen could have changed, and therefore actually the curve has to go up, but instead it is looking like it is coming back down, and therefore for a given value of stress, it has two potential values of strain, and you have to determine which is the appropriate one for a given situation. So that's as far as dealing with heterogeneity is concerned. Dealing with anisotropy, all that you do is to, instead of just dealing with E and nu, or just dealing with lambda and mu, now you introduce certain subscripts to them. So you bring in Eij and nu ij, or similarly you could have a lambda ij and mu ij, if you prefer this kind of a notation. Essentially, you're dealing with that, but this alone again is not sufficient. You might have to deal with various couplings that are involved. For example, in the original isotropic material or metal that we were dealing with, there is no coupling between the normal and the shear. If at all there is a coupling, it's only between normal and normal through the Poisson's ratio if the material has non-zero Poisson's ratio. It could also have zero Poisson's ratio, it could have a negative Poisson's ratio, all the way between -1 to 0.5 positive. So in this kind of a scenario, it is possible that some of the composites in some combinations of directions could have Poisson's ratio which are less than -1 or greater than 0.5 also. Okay, so nothing to be worried about as long as they're still not violating certain basic material principles that we'll probably cover towards the end of the course. But essentially what we are talking about here is that there is a way to handle anisotropy also. Just like heterogeneity was handled by volume average stresses and strains, the homogeneity or rather the anisotropy is handled by introducing direction dependent moduli. And moduli is used in a general sense of various couplings that can happen. The coupling between normal and normal strains is called as Poisson's ratio. Similarly, coupling between normal and a shear strain is also a certain kind of a coupling that can happen, which is not given any specific name, so to speak, but the behavior is very similar to the behavior of the Poisson's ratio. So for Poisson's ratio, we have two subscripts, that is I and J, that is applying the load in one direction and measuring the strain in a different direction, usually an orthogonal direction. And one is the input, the other is the output. The I typically is the first variable is typically in this Poisson's ratio, nu ij. I refers to the input direction, that is where you're loading, and J is the direction in which you're putting your strain gauge parallel to that and measuring the strain, and therefore correlating the two strains. So you measure the strain in the loaded direction, that is epsilon ii, and you measure epsilon jj, and you get the ratio of epsilon jj by epsilon ii and put a negative sign to it. That's what is your Poisson's ratio. Similarly, you can get the shear strains as well through appropriate combinations of sensor placements, and you can get the shear strain, and then say for I'm not applying any shear loads, I'm applying only a tensile load, but the composite, because of the nature it is built up, the fiber angles, etc., it is undergoing shear as well, and therefore I measure that shear strain as a ratio of the normal strain in the loading direction, and that's going to give you that coupling between the shear and the normal. So those coupling factors are also very similar to your Eij, nu ij, etc., in the sense that they are direction dependent. So if you know a coupling between one particular normal direction and one particular shear, that doesn't mean you can use the same value for some normal direction this, even though the shear direction might be the same. So it will all could in general be different depending upon the configuration of the laminate, so or the composite as a whole. The moral of the story that we have here is that there are ways to handle it, and there are more and more refined ways of handling it. People have handled this in the past through certain ways, and we are going to handle it in a far more refined way, but the methodology remains the same. In one case, it's a volume averaged quantities. In the other case, it's direction dependent material properties. As I said, we have introduced these actors in our movie, which are these loads, stresses, strains, and displacements. We have introduced their relationships. Typically, like in a movie, you could have two being partners or lovers, or having an affair, or spouses, or they could be villains, etc. Whatever they are, I'm not going to point who is what over here, but essentially you have those actors. That is basically your load, stresses, strains, and the deformation. Now you bring in the relationship between that. As a director, you're defining how these are going to be defined. Why you are the director? Because essentially you are creating the this problem, or you are giving the problem definition, and essentially this is what you're bringing about. So between the loads and the stresses, you have the equilibrium equations as their relationship. So there's some way in which they're going to relate to each other through the physics or the natural laws, in particular the laws of conservation of momentum. And then between the stresses and the strains is your material, and that's why they say don't show your middle finger, because that's essentially going to cause the stress and the strain. And then you have the relationship between the strain and the deformation, which is essentially your kinematics. So essentially you have talked about these relationships. So whenever there are actors and more than one person, there is going to be politics in that place, be it in academia, be it in industry, be it in a home, or be it in any kind of an institution or nation for that matter. There are going to be conflicts. Now, how do you resolve those conflicts is what we are going to look at from a modeling perspective, but things as always have fallouts on life itself. So there are certain challenges in the modeling, and there are certain conflicts, and there are ways in which conflicts will be resolved. There are certain ways in which conflicts have been conventionally resolved by other people traditionally over a long period of time. There are new ways, refined ways of handling it, which we can show works better, and therefore, which means that the conflict is either resolved quickly, or it is essentially resolved far more amicably to the acceptance of both the parties involved, namely the load, stresses, strains, and deformations, whichever two we are considering at a given point of time. So that's essentially what we are talking about. So let's unfold these challenges and the conflicts, and then we'll look at how to resolve them. So the first conflict that is going to have, one is in red, the other is in green, and that's essentially saying that whatever model you're going to develop, that mathematical model that I want, yes, it has to be accurate. Otherwise, why would I need a model? The whole idea of having a model is that I cannot analyze the reality as it is. It's too complicated for me. So therefore, I need a model to analyze it, to put it on pen and paper or into a computer, into a code, and solve for the problem. I need to have a model. Unless the model behaves as closely as I want with respect to the reality, then it's no longer worth being called a model. And that closeness to reality, how close the model is to reality, is what we call as accuracy. So that is one requirement. The other requirement, usually a conflicting requirement, and which is why I bring in this conjunction yet, is that it should also be computationally efficient. What if it is a very accurate model, highly nonlinear, non-classical model, which even on a supercomputer runs for days, whereas I want real-time solutions either for a design optimization or for the case of the real-time structural health monitoring, which is almost essential on all systems today. Okay, so that's essentially what we are talking about as the computationally efficient case. So why these are conflicting is that as you want more and more accurate models, obviously you have to deal with more and more degrees of freedom, because the original structural mechanics or a continuum mechanics problem, remember, is not like a particle mechanics problem which has finite degrees of freedom, but this has infinite degrees of freedom. But your model is going to have a finite degrees of freedom. So for example, in a finite element method, you introduce elements, you introduce nodes, and each node you introduce certain degrees of freedom, and after you apply the boundary conditions, you remove certain things, or you remove the rigid body modes, etc., and then you are left with a certain set which defines entirely the configuration of the system at any given instant of time, and therefore that is what we call as the degrees of freedom, and their number determines how usually, if it's chosen in an appropriate way, other things remaining the same, the more the number of degrees of freedom that you're dealing with, you're going to have more and more accurate solutions until the results converge, and beyond a certain point, increasing the number of degrees of freedom is not going to give you any advantage in terms of improving the accuracy. We say the problem has converged. So to reach a certain level of convergence, which means you're defining tolerance in certain results that you are interested in, let's say accuracy of 1% in the displacement field, or accuracy of 0.1% in the stress field, etc. So whatever you are defining your tolerances as, what is the number of degrees of freedom you're going to use. So it's from this explanation, it is quite clear that if you want a more accurate model, obviously you're going to have more number of degrees of freedom to deal with. And when you have more number of degrees of freedom you're going to deal with, obviously the size of the computational system that you're going to deal with, even if it's a linear model, it's a matrix that you're dealing with, the size of the matrix from m by m becomes n by n, where n is much larger than m, and therefore the computational time, which is the CPU time, and also the processing after that in terms of the post-processing, etc., everything is going to take time, and therefore you're not going to have as computationally efficient a modeler as you had earlier. So it's very clear that as accuracy increases, the computational efficiency decreases. So if you want to plot in some kind of a quantified way the accuracy and the let's say the computational efficiency, it's very clear that as the accuracy drops, the computational efficiency increases. So that's essentially what we are having, but we want both. So in other words, I define certain level of accuracy that I want. You give me the most computationally efficient model which can do that, and that's essentially what we are going to try to do. But this is right now we are talking only of the challenge or the conflict. We will see how it is resolved as we go forward. So why it is important is, of course, that the accuracy will improve or enhance the utility in real life situations, that which is why we are coming up with a model to have it as close to real life as possible, and therefore it enhances the utility in that. So accuracy has an utilitarian value in it, and for example, if you want to deal with a detailed design problem, or you want to deal with an improvement in the design to delay or avoid failures, then obviously you need to go for a very accurate model, and therefore the utility of that is so good, because it's going to avoid failures, or it's going to do health monitoring for you, or it's going to do certain things which less accurate models cannot do, and therefore the class of problems to which this model can therefore be applied enhances, and that's why we say it improves or enhances the utility to a wider class of problems that you can deal with. The why is computational efficiency important? Again, it's a no-brainer over there. It's quite clear that computational efficiency is important. The reason why I have to state it is because some people keep arguing that, according to Moore's law, the computational systems have also been improving, especially the hardware and the software have improved so much that you have computers which can do far more superior speeds of computation than what they were earlier. So why do we really need to bother about the computational efficiency of an algorithm or the code that you're writing? In a sense, they are right, but in spite of that, if you have a choice of two computational algorithms which are anyway readily available to you, one which is computationally efficient, other which is far less computationally efficient, computationally inefficient, let us say, then which will you use? Because anyway you have the same hardware that you're going to deal with. So even if you have a very fast hardware and software system, you are still going to have multiplicative fold advantage in doing your work with a computationally efficient algorithm as opposed to a computationally inefficient algorithm. Just because you have a number crunching machine which is very, very highly capable, you don't mean you give it problems which just it keeps munching upon. So if it is possible for you to give a computationally efficient algorithm, give it. So in a one-off problem, it might not mean much. It might save me a few seconds. But in a problem where I'm going to use this algorithm repeatedly for iterative purposes, for designing many different components, and then the overall design, etc., then things get more complicated. First of all, the difference between the two algorithms, the computationally efficient and computationally inefficient algorithm in terms of the CPU times, keeps increasing even in the best computation system, and there's a multiplying factor because I want to use it repeatedly. So in any case, it's always a win-win situation. There are certain hardware engineers who are trying to improve the hardware capabilities of computational systems. There are certain operating system software engineers who are improving the operating systems and the application software. We, as the people who understand the engineering aspects of it, the science aspects of it, the maths aspects of it, keep improving the algorithm. So all of these has to work in a partnership, that none of these is kind of going to completely sideline the other two. So all three have their own equal importance, and that's where we come in terms of the potential of providing computational efficiency while retaining accuracy. So of course, computational efficiency, the easiest way to increase it is to reduce the accuracy and give a lesser number of degrees of freedom problem. You would obviously improve the computational efficiency. We don't want to do that. We keep the accuracy as it is, whatever is required for a given application, and then we see how we can enhance the computational efficiency. So in one case, we said it enhances utility in real life problems. In other case, it enables trying out numerous possibilities of advanced applications. So again, it's something to deal with applications, but because you have something which runs very fast, you can apply it on so many different candidate problems on which you don't need to do actual hardware testing. Either non-destructive or destructive testing is not necessary to be done. The specimens don't need to be manufactured, or much fewer specimens need to be manufactured for validation studies, etc. But otherwise, with the mathematical algorithm itself, or the computational implementation of it in a code, you can keep running that code over and over again, and therefore try out various numerous possibilities, or you can do it in a more systematic way towards an optimization algorithm or whatever, and then arrive at most optimal solution, or at least a set of near optimal solutions which can then be tried out experimentally, and one of them can be chosen for the actual design. So many examples I have already kept on pointing out over the lecture as well as in the past. That is, one is real-time structural health monitoring, the other is optimization for design, and then eventually, of course, once you have done tried out all these numerical possibilities, you go through a physical validation either in the lab or in a flight test. So that's the first conflict that we're talking about, which is accuracy versus computational efficiency. That's not the only conflict. There are other conflicts that we have to deal with because as relationships are there are going to be conflicts. So what is the second conflict that we are going to have? The second is between rigor and engineer friendliness. This is usually a conflict between the academia and the industry. The industry usually wants something that can be easily applied by their engineers without too much of an investment on their training. You give us some kind of a black box which is well validated and which we know it works, and therefore the engineers keep using it along with a GUI. GUI is basically GUI, or a graphical user interface for the computational code, and as long as the engineers who are going to use it know how to use that GUI, both for inputs and the analyzing the post-processed results. Of course, drawing inferences is a much bigger art, and it needs a lot of engineering capabilities. But whatever it is, they don't want to know what is happening inside the code or in terms of the theory, etc. Unless, of course, they are more let's say visionary kind of industries which are there for a longer duration, and therefore are investing themselves into a lot into R&D, and therefore want to see what actually happens inside as well, so that they can probably tweak in that and bring in some of their own specific complications which are their own USPs, which might be confidential data they do not want to reveal, in which case they don't want the executable files, they want the actual codes itself that they can play around with and modify according to their requirements. But most often than not, the industry requires engineer friendliness. That is, we're talking of the application engineers, or the people who are going to routinely use your codes. The other hand, if you want to make publications and make conference presentations and still not be ridiculed, you really need to have a certain rigor, the scientific rigor, the mathematical rigor, rigor, how clearly you are stating your assumptions and they're justifying their validity, and then the derivations that are not mincing up things. You're actually going in a logical sequence in trying to arrive at your results. All that counts towards rigor. And once again, I'm bringing in this conjunction of yet instead of and or, but it's essentially like but you should have rigor as well as engineer friendliness. Why are they conflicting? Because if you make it so rigorous, the mathematics is so complicated, the underlying physics principles or physical principles are so complicated that it's very difficult to expect somebody else to understand it, because the amount of time and energy and effort and capabilities they have is very different, because they are for a different purpose. They want to do it in a routine way for something else. So you can't expect them to have that. So when you have something so rigorous, the complications are there in the maths and the physics that many application engineers may not be able to spend enough time to understand that. That is the essential issue. On the other hand, if you have something so engineer friendly that it can mean that unless of course it's purely because of the GUI and the thing is built inside very well, you would have an situation where it's very engineer friendly, but it's not so rigorous, and therefore is not publishable or patentable, or it cannot be accepted in an academic community as something of a useful contribution. So our idea is to resolve that conflict. So how do we go about that? First of all, why it is essential, I've already explained. Rigor, we said accuracy enhances the utility. In the previous slide, we're talking about accuracy versus the computational efficiency. We said accuracy enhances efficiency. Here, rigor, what does it enhance? It enhances the acceptability in academic circles, that is amongst the other professors or other researchers in labs or industries, high-end researchers at conferences or papers, or for at the patent, whoever is the patent granting agency. If you're applying for intellectual property, the ability to get accepted is always higher if you have enough rigor built into the model in terms of the original assumption, starting point, and also the derivation itself and the end results and implementation. So there has to be rigor in that. Only then you'll have academic acceptability. The second thing that we want here is the engineer friendliness, and that engineer friendliness results in wider acceptance, because if you want to sell your product and make it actually usable by the industry, and therefore for practical problems that the society or the nation or the whole globe is interested in, then obviously more and more people should use your software that you create out of this whole thing, or algorithm that you create out of this. So when will they use it? Only when it is engineer friendly. So for wider acceptance and also for quicker implementation. Sometimes the people might say, yes, it's so rigorous, fine, I will accept it, but and they might even buy your software, and then for them to actually start implementing it will take a very long time, because they have to get used to it, understand it, they have to give up their legacy software, and whatever input data files they have for their legacy software, they have to convert it for using it for your software. All this takes time, and therefore the quickness is lost over there. So but if it is engineer friendly, then obviously not only is it wider in terms of acceptance, but it's also quicker in terms of the implementation. That's why we see the need for engineer friendliness. So we have to understand about all these conflicting things or challenges, why it is important first of all, then we will try to address it. If we ourselves don't know why it is important, then why should we even address it? So it's important to see where what you're going and what they're going to do at that particular location with what you've offered. So it's not just a question of offering whatever you want or whatever you have. It's a question of is there a need for it, or can you at least create a need? See, that's the marketing strategy of many of these industries, of many products which come out. There may not be an actual need currently in the society or the market, but they create that need. So by an appropriate, attractive way of marketing strategies, including advertising, etc., you create that kind of a need. So either you have to perceive a real need that already exists, or you create a new need. Like for example, 10-20 years before, nobody saw much of a need for a smartphone, or even for a regular cell phone. Many people running around with pagers, etc. But then you see that slowly the need is created, and almost everybody, irrespective of their economic levels, has these phones, and many people are moving towards smartphones, etc. So we have created a need, and though some of us can, of course, live without these gadgets, there are many we know amongst our own acquaintances who just will suffer a lot even if they don't have it for a few hours, leave alone a few days. So essentially what they have done is through their marketing strategies and through creating that kind of utility through that device, or that we start depending upon that and see a need for it. So that's the lifestyle change that is created, and the need is created. So essentially what we are talking about is that wider acceptance of where people are already using alternate methodologies and where people are not using any methodology at all, and therefore you're creating a need for them to use these new methodologies that you're developing. In either case, it is possible only through engineer friendliness, but academic acceptability will not be there unless you bring in rigor as well. And that's the second conflict. The third conflict that we will deal with here is again between the green and the red that you see here. One is essentially talking about global system level optima. The other is talking about a local subsystem level optima. For a long time, this is what was being done by most people, because aerodynamicists were working separately, propulsion engineers working separately, controls engineers working separately, and we structural engineers working separately. We optimize our own systems without worrying about where it actually fits in. And then you bring in all these optimized subsystems, put them together, the overall system doesn't work as well as you anticipated, obviously, because the principle of superposition doesn't work. So a lot of nonlinearity is involved, and various couplings are involved, which have to be taken right from the upfront in the beginning, which means that interactions between the teams was essential. So it's not only between the interaction between the human teams working on these problems, but the actual subsystems, because in nature all of these are essentially holistic, acting in an integral fashion. And then we are dividing and specializing and creating all these divisions of labor, and each one is so highly specialized that they don't understand something that they think is very good. Let's say an ophthalmologist thinks it's very good for the eye and offers a certain solution, and it might backfire and create some issues with your brain, or it could create some issues with something else, unless they have worked in conjunction with all the other systems that this interacts with, at least on a larger scale, and then you come up with a solution which is not going to have deleterious side effects on the other systems. So this is very classic. There are many classic examples in the medical and pharmaceutical industry about these things, but we are not far behind in terms of engineering systems as well. For long we have been just doing subsystem level optimization and in a local sense, and then assuming that it will be good enough for the global. It's not. So, and yes, at certain point of time the computational systems were not capable enough to handle such complicated system level optimization problems. But now there are computational systems, so why not utilize that? And if you want to utilize that, then yes, you do need to understand how things operate at the subsystem level, but also in terms of that putting that subsystem in the system, it is in a new environment as opposed to an isolated environment. It's not dealing with the free beam anymore in outer space. You are dealing with an actual beam on the ground or on the aircraft, which could be a spar of a wing. Then obviously it has to deal with the skin that is around it, with the transverse ribs that are supporting it at the various locations, and the internal loads that are coming because of the fuel, etc., fuel tanks, etc. All those things are going to be accounted for. So essentially, you need to see where this fits in, and that's essentially what we are talking about as a challenge or conflict over here. So how do we go about doing this? So we need to understand multiple branches of maths, science, and engineering, whatever is applicable to that overall system problem. So whereas as a pure structural engineer, we might understand the mechanical aspects at the solid mechanics level very well. But if we don't understand at least a little bit of the flavor of the fluid mechanics and the propulsion systems and the control systems, etc., whatever solutions we are going to offer might be good to look at by themselves, but of not much practical utility, because the others will reject it, because there are chances that others will reject it because of it not fitting into their scheme of things. So essentially, we should have an understanding of that, and that's essentially what for the 5 MTech students that are there in the class, that's what you did in the previous semester, going through the basics of the various aspects of aerospace engineering, so that you know when you are doing a structural design or a structural analysis, you know where it eventually goes, and therefore you're not blind to those aspects. So you give some, even you may not be actually doing the system level optimization, which is not for individuals usually, it's for big teams, usually in the industry, but also in academia these days. There are a lot of collaborations that happen between different faculty members who work in different fields, and then they get together as a team and offer solutions. But nonetheless, even in the initial stages, these kinds of interactions with the others working in entirely different areas, but which may play a significant role in terms of the environment for your subsystem, will make a difference. So you need to understand at least the basics of the other aspects of science, engineering, and math. Only then you'll be able to accomplish this global system level optimization. So maybe I probably have a little more time. So I'll look at the resolution. So far we looked at all these conflicts that we are talking about. Now we come to solutions. So, and solution or resolution, what we call as resolving a problem. So the solution that we offer should be something that is broadly acceptable, and essentially a resolution that we are talking about, taking a resolution. And what is the best possible one as of today? Just that because we say that this today doesn't mean that it's going to be universally acceptable at all times. So but this is something that is makes sense as of today, and therefore that's what essentially what we are doing. So what is the resolution that we do? The first thing that we do is to develop models as well as tools, which is essentially your algorithms and the computational codes that you write based on your algorithms, which will satisfy all these conflicts that we already talked about. So as long as we understand the conflict, we'll make sure that somehow we will satisfy both. So in other words, we may not be able to maximize both, but given one as a constraint, this is the level of accuracy I want. Anything less accurate than that, I will not accept. Then for that, what is the most computationally efficient algorithm? Or it could be posed in an exactly opposite way and say that this is the amount of time I can afford for my from my CPU time, for example, for a single run of this particular problem. Anything more CPU time than this, I will not accept. So for this level of CPU time, what is the most accurate model that you can give me? So that's the opposite way of framing the problem, but essentially in both cases, you're keeping one as the constraint and the other you're using as to either to maximize or to minimize as the requirement might be. Of course, then there is also possible of a combined thing where you're not putting either one of them as a constraint, but using a weighted average of these two. This is the importance, this much of importance I gave for the accuracy, this much of importance I gave for the computational efficiency, and therefore you work out an algorithm and therefore a code which will help me achieve that. So this is essentially, I'm giving the example of accuracy versus efficiency, but the same thing applies to the other two or three conflicts that we talked about as well. So once we have these, it should satisfy this. The simultaneously is important. So both those seemingly conflicting environments that we want it in, like for example in academics as well as in the industry, we want something that is, especially we as academic researchers, many of your PhD students, the MTech students will be doing your MTech projects, and eventually in your careers as well, you will see that there are things that need to be accepted both by the industry as well as the academia. Academia because you want to publish or patent or be known in your academic professional circles for what you do, and therefore be of value. But the other thing is, if it's purely theoretical academic research that you're doing, which is not finding any applicability in the industry, at least in your lifetimes, there are many such situations where for the entire lifetime of the scientists, their findings were not of any significance, but much after their death, people are finding their applicability. One classic example is, of course, Srinivas Ramanujan's mathematical treatises, many of which are now being used to understand black holes, which even the concept of the black hole was not there during his time, but he derived the mathematics for it. Usually it happens the other way around, that you have a certain problem that you observe in physical reality, and then you try to come up with mathematical algorithms to do that. But sometimes it could happen the other way around. But essentially what we are trying to do normally is to see that can we have something which can cater to both the academic rigor as well as the engineer friendliness, something which is both accurate as well as efficient, etc., which can have a subsystem level understanding as well as not violate the global system optima that we are actually all as a team focused upon. So that's all that we want to do. So how do we do this? We establish first accuracy. How do we go about doing that? We establish accuracy through the variational principles. There are lots of variational methodologies, starting with Maupertuis, then going on to Lagrange, Hamilton, and Berdichevsky, etc. But essentially, they're all operating on stationary principles or variational principles. The calculus of variations, where functionals are involved, usually in terms of the energy fields, and then you're trying to come up with the minima or at least the stationary value of those in order to solve that. And most of that, because it's kind of modeling the very best known physics aspects of it already, therefore the accuracy is guaranteed, at least from the current level of understanding of the physics of the problem. So therefore variational principles guarantee that. Another way in which the accuracy is guaranteed is, of course, the geometric exactness. That's why we deal with the so-called geometrically exact beam theory or geometrically exact plate or shell theory. The whole idea is that where you can do geometrical exactness, in other words, the kinematics, no assumptions are made, you might as well do it. So that's essentially also going to improve the accuracy. So one level at the energetics level. So this is improving it at the energetics or materials level. Whereas this is improving the accuracy from the kinematics level. Because they're all building blocks for the entire problem. Somebody had a question? Okay, so all these are building blocks, and so you do not want only one aspect of it to be accurate enough. The other is going to completely scuttle the whole advantage that you have gained, because any chain is as strong as its weakest link. So if there are a chain is made out of multiple links, and one link is connected to another and so on, it comes back and makes a full circle. On a cycle chain, for example, or a motorcycle chain that you might have, or belts, for example. In all of these situations, if there is one link which is weak, or in the belt one particular location that is weak on the belt, then all the others locations, or all the other links in the chain might be very strong. No use, the chain breaks because of that one weak link. So essentially you are trying to ensure that all those ingredients into your theory, which is essentially those three that we saw in terms of the equations, the equilibrium equations, how well is the physics understood, the constitutive law, how well have the experiments been conducted to get all the material properties of interest within a certain probability. So it could be not deterministic values, but probabilistic values for them in terms of probability density distribution functions, or PDFs. And then of course the kinematics, where fortunately we have reached a stage, even 30-40 years back already, reached a stage where we can do exactness. So there's nothing much to do beyond that. That's why we already have a geometrically exact theory in place. So there's not much improvement we can do. But can we make improvements in a better understanding of the physics to understand the equilibrium equations or the natural laws better, considering all the other force fields, especially like gravity, etc., which have not yet been understood as well as, let's say, the electromagnetic field, for example. And then most importantly in the constitutive law, because that's where still we are doing a lot of empirical work, and depending too much on the experiments. Still we do not have a theoretical understanding of how the stress depends on the strain or any other material behavior. We always have to go ahead and do certain standardized tests defined by various agencies like ASTM, etc., and then arrive at the things. Yes, that's a well established and validated way of doing things, and people have spent their lifetimes, big teams have worked on it, and taken it to a certain level. But we also, as theoreticians or computational people, we need to see what we can contribute there. There has been some work done through molecular dynamics, etc., to understand the material behavior, certain material science models, the way you design a material upfront entirely in a computational sense, computationally designed materials, just like there are computationally designed drugs for pharmaceuticals, for example. So similarly, you come up with these kinds of things. But still, there's a lot of room for scope for research in those areas to better understand, and especially complicated things like composites, etc. There's even more room to understand things better. But essentially, accuracy means that the underlying physical principles, the geometry, etc., have to be at least accurate or asymptotically correct, if not geometrically exact. So that's essentially how we are establishing the accuracy. So then the other thing which was conflicting with that, now that accuracy has been established at least to a certain acceptable level through variational principles, geometrical exactness, concurrent multiscale modeling. You can include number 3, 4 over here, apart from 1 and 2, the non-deterministic modeling, concurrent multiscale modeling, etc. So you have many ways of doing it. Now, computational efficiency. One is the nonlinear domain decomposition that I talked about. But in the way that we are going to do it in this course, essentially is through asymptotical correctness. So instead of, we are not always chasing exactness. Exactness, it could also be a sour grape story, because many a times, because just like that fox which was trying to grab the grapes in the vineyard, and it was too short and was not able to reach the grapes, and therefore after trying a little bit, it gave up and said, well, the grapes are very sour, so I don't want to take that anyway. So it's not just that. in some cases, an exact solution might be possible, but still it might be too much of effort to deal with that. So even there, asymptotical correctness helps. But in most situations, it's because of the fact that you are not able to reach it. It's sour grapes. Your exact solution is not possible with the level of mathematics development today, because mathematics is also an emerging field where people are improving mathematical techniques. That's why you have mathematical researchers as well in mathematics departments, like including in IISc. So we keep improving our mathematical techniques. But with the given current level of the mathematics that we have, the computational efficiency can to a large extent be increased by the asymptotical correctness and the dimensional reduction that is ensuing because of the application of that variational principle along with the asymptotical approach. And therefore, instead of dealing with a 4D problem, we are dealing with either a 3D problem or a 2D problem, or for a particle method, you're dealing with a 1D problem where only the time is of consequence there. So once you do dimensional reduction, it's quite clear to see that the number of degrees of freedom have dropped, and therefore computational efficiency has increased. The asymptotical correctness also, you can see you have dropped off the higher order terms in the governing energy functionals, and therefore you're dealing with a less complicated energy functional. Obviously, the minimization or stationary principle of that is going to be much easier to be achieved both in an algorithmic or as well as a computational code implementation sense, and therefore once again the computational efficiency is achieved. So that's essentially what we are going to do in terms of the resolution. And of course, we are going to combine these techniques along with these techniques, and which is what we have as the variational asymptotic method, which we'll try to look into from the next week onwards. Thank you very much. If anybody has any questions, they can stay back and ask me. I'll wait.
Sir, I have a question.
Yes, please. Yeah.
Sir, suppose yes, I have a suppose I have a perfectly rigid material, and I am making a beam out of that. Let's say I have a simply supported beam with a infinitely rigid material. So and I'm loading it, and so how that beam is going to handle that loading? I mean.
So it's going to see, in reality, there's no such thing as a rigid body, but assuming that it is there, and this is a rigid body, so it has to behave like a rigid body, which means that the simple supports that are there, they have to give way. So if the structure itself is rigid, then the supports that are going to be there, the load transfer is going to take place through the structure. So let's say this is the simply supported beam, that pencil over here, and my fingers, the thumb and the pointing finger here, are the simple supports. And suppose this beam is rigid and I'm applying a concentrated load over here, all that it's going to have is just a load transfer, because whatever force F I apply here is going to be transferred as F1 and F2 depending upon the location at which this F is over here and here in terms of the moment equilibria apart from the force equilibria. So I can determine the F1 and F2 which is acting on the simple supports, and therefore the simple supports are going to give in some way, because see, this is entirely a hypothetical problem that in reality there is no rigid body nor the simple supports. But once you have defined it in such in that kind of a way, it's just that the load transfer is going to take place without this taking any stress whatsoever, because it's a rigid body. It's only when it's a flexible body it's going to flex and create certain stress levels at different locations. But otherwise what's essentially going to happen is that it's not going to be able to deform, which if it's not going to be able to deform, it doesn't have any strains, and already it's a rigid body. So your stiffness matrix is let's say the corresponding diagonal term is infinite. So that's what rigid essentially means, that the diagonal, or at least one of the diagonal terms is infinite, and therefore you're multiplying infinity with 0, you're supposed to get a finite stress value. So it's all in the question of limit that you're essentially dealing with this particular problem, but recognize that this is a hypothetical problem and therefore not of much practical significance, but still it's a good thought experiment to conduct, because all these thought experiments help us to understand not only these subjects but also the real life flexible entities as well, which is going to have a certain finite stress. So the other thing is, it's so flexible that, like, let's say a membrane doesn't have any bending stiffness. The ideal membrane has a 0 bending stiffness, and therefore it flexes as much as it wants. So in either case, there's a way to give up on stress. So these are the two extreme ways of approaching liberation for this structure. One is to become fully rigid, which is infinite stiffness, or to become fully flexible, or which is 0 stiffness. One of the diagonal elements of the matrix, stiffness matrix, going to 0. So it's no longer positive definite, it's positive semi-definite, and therefore you have another way of approaching the whole thing. But essentially, you know that what you are going to deal with in a finite element implementation of this system is that you are going to get rid of these rigid body degrees of freedom, because this body essentially is going to have only the rigid body degrees of freedom, which are essentially its 3 translations and 3 rotations. If it's defined within a plane, then essentially it's 1 rotation and 2 displacements that it is going to have, and that's what you have to deal with. There's nothing like the elastic deformation in between creating other aspects to it, but it's purely an imaginary problem. There's nothing real about it. It's just that it helps us understand things better, both for the structure as well as our life. Nilesh?
Yes, sir. Sir, and let's say, because there will the strains will be 0, and corresponding with that will not be stresses, because stresses are are created because of the strains only.
And so that's what I'm saying. It's a multiplication of infinity with 0. So it's possible that you can still have a finite stress, but it's a question of how you're going to take those limits. So it's not, so you approach the material in the material sense that the material becomes rigid. That you have, see, how do you implement it in a numerical sense? An infinite value is by putting a very large number, right? So in other words, on the diagonal of the stiffness matrix, that whatever you want to make it as rigid, you will make it as a very large value by some 10 power n times the largest other diagonal element, and therefore where n is of course a positive number, much larger positive integer, and then you essentially are creating a situation where it behaves almost like it. So you can approach towards a rigid body through enhancing the stiffness more and more and more and more. So that's one practical approach to kind of leverage your problem. But essentially what's happening is that you have a 0 quantity and you have a infinite quantity. The product, it can be finite, because 0 into infinity, though it's not defined, it can have a finite value. It need not necessarily be another 0 or necessarily be infinity. It's a question of how quickly the strain is approaching 0, how quickly is the stiffness, diagonal term of the stiffness, corresponding diagonal term of the stiffness, how quickly is that approaching infinity. So if one is approaching, let's say the stiffness is approaching infinity much more quickly than the strain, there is one way of approaching the problem, and which means that this is the dominant thing that is going to happen. Otherwise, if the strain is approaching 0 much more quickly, then that becomes the dominant thing. So essentially, you have to deal with it in the appropriate sense in the algorithm that you develop.
Yes, sir. Thank you, sir.
Okay, welcome, Nilesh. Anybody else? Any questions? Okay, thank you very much then. We'll meet next week, Monday. Thank you. Bye-bye.
Thank you.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Most welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Most welcome. Come on.
मृत्युञ्जयमन्त्राः।
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात्। ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे। मृत्यवे स्वाहा मृत्यवे स्वाहा